Okay, good morning, everyone. Let's just give another few moments for people to arrive as they are arriving. Okay, so let me tell you about the format for today. Oh, looks like we have someone else. Just flew off my radar. Okay. It's really weird. Sorry, I just had someone who I thought wanted to join, but then it disappeared. Okay, so here's the format for today. It's an exam review with any questions you want to ask about exam 2. We had a really nice discussion in my other class about everything from cutoff scores to choosing the right test to confidence intervals. So like I said, any content questions you want to ask about is fair game. I will tell you that here's the setup for exam 2. It will be 50 minutes long. You will get from 9 a.m. to 11:59 p.m. to take the exam. So just choose an appropriate 50-minute slot for yourself because once you start the exam, you can't go back and forward to it. You have to take it in the allotted 50 minutes. Also, for this exam, I am requiring a note sheet. So the note sheet is worth up to 5 points for you. And there'll be a slot to actually post the note sheet in. So please make sure you don't forget to do that. And that's pretty nice, easy way to get 5 points by creating a nice note sheet. Could be front and back. And it has to be unique though. You can't copy from another student. It has to be your own note sheet. Okay. All right. So I will at this time open it up for, oh, and also one more thing. The format of the questions will be very similar to last time. In that, I mean, there will be up to 25 questions. Up to 2 of those will be fill in the blank. The rest will be multiple choice. And I am planning on a bonus question for this time too. So, my opinion, you should always take a stab at all questions, even if you're not sure, especially multiple choice, even fill in the blank, in my opinion. But I had a student once who was, kind of the last one in the test and, had to finish it off. And the student had a complicated question ahead where they had to do some calculations. I mean, it was, it would have taken another 5 minutes, let's say, right? And, they didn't have time, so they just selected something. They selected the right answer. So they got credit, so that's how it goes. So I definitely recommend, choosing an answer even if you're not sure. Okay, having said all of that, please, as you have questions, please go ahead and chat them into the chat box, and I will be happy to respond to them. You have your concept checklist. You can look at that. You have your formula sheet. You have your tables. Those are all the things I'll give you access to on the exam as well. So feel free to look at those. And yeah, here's our first question. Once homework 3 is closed, can I upload the answers? Yes, I can do that for you. No problem. Yes, I get it. So you can actually study them. Let me find a good way to do that. I actually think I found a good way to do that. I just thought of it. Yeah, no problem. I'll take care of that for you. When to use each test. Let's talk about when to use each test. Okay, that's a great question. So I just posted this, that this came up in my last class too, like what might be some good practice problems to go through over the weekend, before Wednesday, if you'd like. So I just posted some practice problems with some answers, and I'm going to look at those with you because I think that's a good way to talk about which test to use when. So let me share that with you. Give me 1 second. And then you can kind of, I'll just go, so that's just the first question for each one is which test to use. So let's talk that through. And then, if you guys want to work through the rest, you're welcome to. You're welcome to look at the answers. I posted those too, whatever you like. Okay, so let's look at the first question here. You wish to test a new treatment for major depressive disorder. You obtain a sample of 6 participants. These 6 participants complete a well-known inventory for major depressive disorder before and after the new treatment. Higher scores indicate higher levels of depression. The scores are below. You wish to know if there's any difference between the scores collected before treatment and after treatment. Assume alpha is 0.05. Okay, what do I see immediately? I see 1, 2, 3, 4, 5, 6 participants, and I see 2 scores for every participant, right? Participant A got 7 before treatment, 8 after treatment. Participant B got 2 before treatment, 9 after treatment. If I see 2 scores per participant, I know it's a dependent samples t-test. Okay, that's a hard and fast rule. So 2 scores per participant is dependent samples t-test. Okay, all right. Next one. If I can get this thing to scroll. Hang on a second. Yeah. Being uncooperative with me. I'll just go this way maybe. All right. Oops. Question, if this will ever work. Question 2. You are exploring the relationship between caffeine intake and response time in a driving simulator. You have 36 participants drink a 6-ounce cup of coffee and have them complete a driving simulation task. The group obtains a sample mean of 392 milliseconds, and you know that the population mean is 400 milliseconds, and sigma equals 40. You wish to know if this sample's mean reaction time is different from the population mean. Aha, I'm comparing sample mean to population mean. Use alpha of 0.05 and assume the original values or scores have 1 decimal place. So let's look at this one. I've got a sample mean and a population mean. Aha, it must be either the z-test or t-test for a single sample, because those are the only 2 that compare a sample mean to a population mean. Okay, now which one is it? Well, I'm given a sigma. I'm given a sigma. This means population standard deviation. If I am given any form of a sigma, look for this symbol or look for population variance or population standard deviation or population standard error of the mean. If I see any of that, it's a z-test. Okay? If I see any of that, it's a z-test. Okay? So if I'm given a population variance, a population standard deviation, a population standard error of the mean, which means I see a sigma squared for population variance, a sigma for population standard deviation, or a sigma of x bar for a population standard error of the mean, z-test. Had this either just given me raw data or given me an S or S squared or S of x bar, it would have been the other one, the t-test for the single sample. Okay, so let's now press on to the third example. Oops. Sorry, for some reason my regular scrolling isn't working, so we're going to do this. Okay. The monthly rent in dollars for a 2-bedroom apartment in the borough was recorded for a sample of 10 apartments. Okay, here's my 10 prices for my 10 apartments. Do these data support the claim that the mean monthly rent for a 2-bedroom apartment is higher than $775? Use alpha of 0.05. Okay, great. So this one I really like because it's phrased, I think, a little bit closer to how the homework is phrased. So once again, I'm comparing a sample mean to a population mean. Now, can you find the population mean if you look at this? It's the average mean monthly rate for a 2-bedroom apartment. It's $775. That's my mu. That's my mu. What's my X bar? The mean of these 10 apartment prices. What's my N in this case? 10. I have 10 apartment prices. It's not people this time, it's apartments. But it's still, that's my sample, is these 10 apartments. So the sample mean is whatever the mean of these numbers is. My population mean, my mu is 775. That's like, as I said, that's my X bar. In this case, I would have to figure out the variance from scratch. If I was given that, I could move on to the next step. Okay. Now, I'm just going to go up for 1 second because I want to, or I don't even have to go up, but I want to ask you for a second, if you were to calculate the t-test for a single sample, how many decimals would you have in your final answer? How do you know? Well, the way you know is that this has no decimals. These are all integers, right? There's no numbers beyond the decimal point. So my final answer would have 1 decimal. I just add 1 to that. And in the previous problem, if this lets me scroll up and is kind, I said, you assume the original values of scores have 1 decimal place. Okay, if the original scores have 1, I add 1 to that, I get 2. That's how many should be in my final value, my final T or Z. Okay. Now here's our 4th question. And I guess you're probably already knowing what it's going to be, but let's go through it anyway. You wish to know if there are differences in the size of butterfly wings in 2 species of butterflies. 2 different species. You obtain 2 samples, 2 separate samples of measurements of the size of butterfly wings for the 2 species. On average, is there a difference between the size of butterfly wings in species A as compared to species B? Assume that alpha is 0.01. 2 separate, 2 independent samples, species A and species B. What is that? It's the independent samples t-test. How do I know? I'm comparing 2 samples. It's 1 score per participant, and I have 2 samples of data. That's how I know it's the independent samples t-test. All right, I'm going to come back to my chats now. Yes, there is a YouTube exam review that's up there, and I think I'm also going to post this up there in case you want to look at this again a little later. Okay. Okay, so let's talk about this next question, and this has to do with z-score tests or z-tests. To determine if it's significant and reject the null, you calculate the z, and then you compare it to what's in the z table. And the question is, do you beat what's in the z table? If you beat what's in, that's right. You calculate the z greater than the z table, and that's it. That's all you need to do. Okay. Confidence intervals, as was asked here, is that what you have to do in addition or instead of? And the answer is it's really the same thing. So you just should be doing it twice. And since I think confidence intervals are a little more complicated, if you're asked a z-score, z-test question, I would go ahead and just calculate the z, compare it to what's in the table, and try to beat what's in the table. Okay, so I'm going to move down to the next question. Okay. Okay. So there's a question about the homework. And can we talk about some of the homework questions? Yes, we can. I'm going to see if some of these other questions are a little quicker to answer, and then we can look at a couple of the homework questions together and kind of talk through how we would approach it. Okay, so we'll do that. Okay, so then the next question is, yeah, okay, 2 questions I'm not surprised by. What's the confidence interval then? And does it just reassure the answer? In a way, yes, because we only learned about confidence intervals for the z-test. So if you actually calculated the z-score, okay, and then you calculated the confidence interval, and they should both produce the same decision, either reject or not reject. Okay, because all they're doing is asking the question in different ways. Okay. And we only do 95% for the confidence interval, either 95 or 99. So again, this could be a memorization thing. If it's 95%, it'll be 1.96 for your number. If it's 99%, it'll be 2.58. So those are the only 2 you ever have to worry about. Now you could look that up in the z-table, but I think people sometimes struggle with the z-table and find it a little bit confusing. And we're just about to actually look at the z-table because someone just asked a question about that. So let's do that. And then we'll actually see the 1.96 and 2.58 and how they appear. And you can decide whether you want to actually, look at the z-table or memorize or write down a few of the numbers from the z-table. So I have to find my z-table. Okay, I'm going to share that with you now because that's the next question that came up. Okay, yeah. So let's look at that homework. I will say the homework is good, in my opinion. I think it's a good prep for the exam as well. But we will look at it as soon as I'll make it the next thing after the z-table thing here. Okay. So here's our z-table. To find a cutoff point, you go to percentile. That's where we're going to start. Now, if our alpha is 0.05, and if it's one-tailed, we're going to go and find 5% in our tail. So let's scroll all the way down to where we find, here it is, 5% in our tail. And it's got to be one of these 2 numbers. And by convent, because these are very close to 5%, right? 5.05, 4.95. By convention, we choose this one. We go to the left, and our corresponding number is 1.64. Now, depending on how the problem is phrased, it may be positive 1.64 that you're trying to beat, or negative 1.64 that you're trying to beat. Not both, one or the other. Now, if it had been an alpha of 0.05 again, but this time it's 2-tailed, now you're going to have 2.5% in each tail, right? I divided that 5% into 2 pieces. So you have 2.5% in each tail. Okay. So I go to look for 2.5% in the tail. It's right here. What's the corresponding number? 1.96. Aha, we just saw that with the confidence interval. This time the number to beat is either, you get a choice, positive 1.96 or negative 1.96. You can either be bigger than 1.96 or less than negative 1.96. You got to be more extreme further in the tail than those 2 numbers. Okay. And just like a confidence interval that has 2 sides, a 2-tailed test has 2 sides, and that's kind of why they're the same. Okay. Next, the only other possible thing that can happen is we have an alpha of 0.01. Now, if it's one-tailed, we're looking for 1% in the tail. So let's keep looking, keep scrolling down until we find something close to 1% in the tail. Here it is, 0.99. I go to the left. The corresponding number is 2.33. 2.33. That'll either be positive or negative, not both, one, depending on the phrasing of the problem. And finally, it could be 1%, alpha of 0.01, 1%, and it could be two-tailed. So we divide that by 2. We're looking for 0.5. Here it is. This is the one we take, the 0.49, and the corresponding number is 2.58. 2.58. So if you don't like the table, really the only things that are going to come up on the exam this time are going to be either 1.64, 1.96, 2.33, or 2.58. Now, I do think it's always better to be comfortable with the table, to be able to find something, but if you're really struggling with that, it might be worth it to just decide to hang on to those numbers. But hopefully this explanation helped a little bit in understanding how to approach that. Okay, so okay. So I said I would do the homework next, and then we'll talk about null and alternative, and we will also talk about symbols a little bit. I did do a symbol review, by the way, in the exam review, but I think it's worth talking about here too. So homework. Let's take a quick look at the homework. So give me a second to get to the right space. Okay. Yep, so I want to preview the homework here. So this one is, and I'm generally hearing, I'm not going to look at all the homework. I'm generally hearing problems from the latter part. So I think I'm just going to focus on that. Oops. It's coming up. Give me a second. And I think problems start with, yes, 20, not surprising. Okay, so this is when we get into the scenarios and you have to choose which one it is, etc., etc. Okay, so let me share this first. I don't think I shared it yet. That's not helpful if I don't. Okay, so here's problem 20. By the way, the question should be in the same order for all you guys. The answer choices might be slightly different. So a large population of people were shown a video of a collision between a moving car and a stopped car. Okay. Each person responded to how likely the driver of the moving car was at fault on a scale of 0 to 10. Okay, we have a normal curve, and our population mean is 5.4. Our population standard deviation is 0.8. At this point, you should know which test it is, because I was given a population standard deviation. And what I say about that, if you recall, I said if I give you a population standard deviation, any form of sigma, it's a z-test. So that's what this one is. Okay. 15 randomly selected individuals are tested in a condition in which the wording of the question is changed to, how likely is it that the driver of the car who crashed into the other was at fault? These participants gave a mean fault rating of 5.8. The question the researcher's interested in, did the changed instruction significantly increase the rating of being at fault? Assume alpha is 0.05. Okay, so next question we can ask ourselves, is it one-tailed or two-tailed? Did the changed instruction significantly increase the rating of being at fault? Well, it's one-tailed, right? Increase. So we're given our population mean. Where is our sample mean? Oh, right here, 5.8, right? These research participants, these 15 research participants gave a rating of 5.8. Okay. Here we go. So how do I get the Z cutoff score? Well, I know my alpha is 0.05, and I know now that my it's a one-tailed test. We just talked about that, so hopefully you can figure out the Z cutoff score from there. And I said that things were going to increase, right? I said that this was going to increase, so I'm going to be eventually subtracting 5.8 minus 5.4. Because it's one-tailed, I might also ask myself the question at this point, just to know, just to have it in the back of my head. Okay, well, they claimed that the wording was going to increase if the other was at fault. Is 5.8 bigger than 5.4? If yes, I'm okay. If no, there's no way I'm going to reject the null. Okay. And then question 21 gets into how the actual calculation of the Z-score. Okay, so I think let's talk about it in general terms. If you are given a variance, and for all of these problems you were given some form of variance, either a variance or a standard deviation, then if you have a Z-test or a t-test for a single sample or a t-test for dependent samples, your next step is calculating the standard error of the mean. Okay. I already was given my mu and my x bar. All I have to do is calculate my standard error of the mean, which in this case would be sigma over the square root of n.
Is the standard error of the mean and standard deviation the same thing?
No, good question. Standard deviation is sigma for population, and it's the amount of spread. Standard error of the mean is when you take that sigma and place it over the square root of n. And that gives it to you, in essence, it's trying to give you spread within a population, if you will. Okay, it's trying to give it to you like if you had run for the standard, for the sample, let me try that one more time. For the sampling distribution of means, if you remember how that's narrower, this is really giving you the spread within the sampling distribution of means once I take that 0.8 and divide by the square root of it. Okay, all right. So I would, as we said, to calculate the standard error of the mean, I would take this over the square root of n. And then for the, once I had that answer, I would plug in 5.8 minus 5.4 over that standard error of the mean. And that would be my answer here. Okay, all right.
Can you repeat that one more time?
Of course, yes. So the process of calculating this one, I would take my, I need to calculate my, I'm already given my 5.8 and my 5.4. I'm already given 5.8 is the x bar, 5.4 is the mu. I have my standard deviation. I need to get my standard error. I take 0.8 over the square root of n, which was 15 in this case, right? Because we had 15 people, 15 randomly selected individuals. So I take 0.8 over 15, sorry, 0.8 over the square root of 15, get that answer. Then I take 5.8 minus 5.4 over that answer. That will give me what I'm looking for. Okay. So, quick point. I just want to raise this point because I think it's important. Had I given you the variance instead, had this been sigma squared, what would I have done then? Well, then I would have taken the square root of 0.8 over the square root of n, over the square root of 15. If this had been sigma squared, because that's variance. And if we remember way back when, standard deviation is the square root of variance. Okay, all right. So let's, what's the next question here? What decision would you reach? So what I'll say about that is now what we're doing is looking to see if we've already found out the direction was correct. 5.8 is indeed bigger than 5.4. So yay, the direction's correct. Now it's just a matter of, did I beat what's in the table? Did the number I got in, let me put it this way. Did the number I got in 21 beat the number I got in 20? That's what 22 is asking for. Okay. Now let's take a look at the 23 setup. Okay. Suppose a candidate running for sheriff in a rural community claims that she will reduce, okay, we're looking for a reduction, the average speed of emergency responses to less than 30 minutes, which is known to be the average population response time. So what's 30 here? What is 30 represented by? That's actually my population mean. That's my mu. Now, the actual standard deviation of the population of response times cannot be determined. Oh, I'm not going to be given a sigma or a sigma squared or something like that. Okay, good to know. It's not a z-test because there's no population standard deviation, population variance, nothing like that. Okay, thanks to the campaign, she's elected sheriff. The sample response times in minutes for her first month in office are, and we're given these, I believe, I believe it's 10. Yes, 10. These 10 sample response times. So what I'm looking to understand here is if the mean of these sample response times, this is my sample now, right? Is the mean of these sample response times, so I had to get an X bar here, I have to get an average, going to be less than 30 minutes than my mu? Is this X bar less than 30? Now I've taken the step of already giving you the sample variance. So good time to bring up a symbol. What's the sample variance symbol? It's S squared. It's S squared. So I'm given S squared. Okay, the researcher's interested to know, did she keep her promise of reducing the average population response time? So again, I want to know, is X bar here less than 30?
I'm sorry, I just have a quick question. You said you said variance is S squared.
Yes, sample variance is S squared.
Then what is is it theta with like the square root of X bar? I thought that was variance.
You mean sigma squared? That's our
Yeah,
population variance. So
sigma squared of X bar is population variance?
no, plain sigma square is population variance. Plain S squared is plain sample variance. Sigma square, the sigma of X bar is the population standard error of the mean, and S of X bar is a sample standard error of the mean. So those are 4 different symbols. So how about after this, we take a look at symbols together and kind of like see if we can maybe pull that together a little more.
Okay, sorry, thank you.
No, that's fine. That's fine. I'm glad you're asking, but maybe just to kind of keep on the same track, maybe we'll do that piece right after this. Okay, so sample variance is given here. So this is our S squared. So we're given variance. So what's the next step now? Same thing, calculate standard error of the mean. But before I do that, I guess I'd like to know which test this is, right? That's going to be important. I'm still comparing an X bar to a mu. I'm still comparing a sample to a population. However, I'm not given any sigma squared, any sigma, anything like that. I'm not given a population variance. So this is a t-test for a single sample. Okay, so I'm going to skip the null and alternative here. I think most of you are comfortable with that. I can come back around. I think there might have been a question, so we can always come back around to that, but I want to make sure we get to these other pieces here. So determine the Z or t-tabled cutoff score. That's again, now we know we have a t-test for a single sample. We go to the t-table and find our cutoff score. Okay. All right. And we know we have we're talking about decreasing, so it's one-tailed. We're given an alpha of 0.05. Our DF is 10 people, minus 1 is 9. Okay. And next we have to actually calculate the test value, which is going to be a t-value or t-score. So how do we do that? So basically what we're going to do, first of all, we better get our mean over here. So we'll get our mean. Then let's go ahead and get our standard error of the mean for our sample. How do we do that? Now this time it's S squared. So we better take the square root of S squared over the square root of N. Before it was simply if this had been S, if this had been a standard deviation, it would just be this number over the square root of N. But because it's a variance, because it's S squared, it's the square root of S squared over the square root of N. And then finally, we'll take our X bar minus mu. We're hoping it's negative, right? Because we want to see that this number, the X bar, is less than the mu. We're hoping it's negative, which means our cutoff score should be negative, by the way. Our tabled score should have been negative. And then we go ahead and take this minus this over our answer for our standard error of the mean. Okay. All right. Once we do that, we can compare our two again. And we are hoping once again that 26 beats 25. Let's go through this last set. Now this time we have 5 sophomores that were given an English achievement test before and after receiving instruction in basic grammar, and their scores are as follows. Okay, and we're hoping for higher scores after instruction. We're hoping for higher scores after instruction. Okay, once again, we have a one-tailed test. So I've got 2 scores per participant. It's got to be dependent samples t-test. What does that mean? Okay, that means I got to get my difference mean, which means I got to subtract. I'm hoping after is higher than before, so I'm going to subtract after minus before. I'm going to subtract 16 minus 21, 21 minus 17, 15 minus 18, 17 minus 16, and 10 minus 13. I'm going to take those numbers and take the average. I'm hoping that number's positive, but I think it's going to be negative. But I'm hoping it's positive. I'm also given the variance of the different scores. I'm given S squared D, okay? Or just plain old S squared if you prefer that language. What do I got to do? Same business. I've got to calculate my standard error of the difference mean. I take my square root of 13.2 over how many people did I have? 5 over the square root of 5. Why did I take square root of 13.2? Because it was a variance. Had it been a standard deviation, I just would have taken 13.2 over the square root of 5. But it's not, it's a variance. Now, once I have this, and I calculated so I figured out my cutoff score in 28. I looked at my table, and that was based on an alpha of 0.05, a DF of 5, and a one-tailed test. Now, in 29, I calculated the test value, and in 30, how do I decide if I'm going to reject? Well, two things. One, I've got to beat what's in the table. I need 29 to be more extreme than 28. And I got to have the direction right. In other words, my after scores should have been higher than my before scores. If my after scores are not higher than my before scores, no way. I'm not going to reject the null. Okay. All right. Let me look back into the chats real quick. And there was a question about what number we use to find the cutoff. Okay, so let me look at a few of these chats. Sorry, I had to go back a little bit. We went through the homework. We want to review symbols. We want to look at null versus alternative hypotheses. Okay, so let me first answer the question about the cutoff. So I think we talked about this a little bit, but I'm not sure I understand the question exactly, because I'm not sure when it came up precisely. So if it's a Z, we talked about the 4 cutoff scores. And if it's a T, did we not look at the T table? Maybe we didn't. Let's look at the T table real quick just to make sure we're on pace with that. So I'm going to switch my share. Yeah, I think we didn't because I'm not seeing it on T. Switch my share to the T table. Let me talk about that real quick. Here's what I need. Okay. So for T table, you first decide if it's one-tailed or two-tailed. You decide if you're on the left or right side. Next, you have to know your alpha. 0.05 or 0.01. It'll never be 0.10. And finally, you have to know your degrees of freedom, your DF. So if you are using a t-test for a single sample or a t-test for dependent samples, your DF is n-1, sample size -1. If it's a t-test for independent samples, which did not come up on the homework, by the way, if it's a t-test for independent samples, it's sample size 1 plus sample size 2 minus 2. Okay. So that's how you figure that out. Actually, I think we did talk about t-test before z-test, and I'm thinking about it. But that's how you find the cutoff score to compare to. Okay, if that doesn't answer it, please message back in. Next, we want to talk about null and alternative real quick. So I think I will go back to the homework to talk about that. And then we want to talk about symbols. So let's do those two things. Let's make sure we get to both of those. So now I have to remember where we actually talked about this, the null and alternative, so I can show you an example. So the alternative, I mean, I guess it doesn't matter. Let's just take any of these examples. Let's take this one, in fact. The alternative you pretty much get out of the problem phrasing. Okay, what does the researcher want to know? The question the researcher is interested in is, did the changed instruction significantly increase the rating of being at fault? So what's my alternative hypothesis? The changed instructions significantly increase the rating of being at fault. What's the null? The changed instructions did not significantly increase the rating of being at fault. So alternative is what the researcher believes. The null is not that. Not that. Okay. Now, let me press on to symbols. And I've just got to locate where that would be. And I think it's in what I just did. So it's important to talk about. So I think it's worth it to just go through symbols real quick. And it was in the lecture I just did this morning. So I think it was here. Let me see if it's in here real quick. Yes. Okay. So let me give you a new share. I can share this with you. Okay. So these are the symbols. So I think one of the most important things we can do is distinguish between population and sample. And we did this kind of at the beginning, but I know it's been a while. So population is everybody, right? Sample is just a small group of people we have access to. So when we talk about population mean or mu D, it's everybody. That's the average, that's the typical, that's the known mean for everybody. The sample mean, the X bar or D bar, is the sample mean. It's just the mean for our sample. Okay, well, what's the variance for everybody? Sigma squared. And the standard deviation, which is just the square root of the variance, the standard deviation for everybody is sigma. And while we're on that note, if we take this over the square root of n, what do we get? Our sigma of X bar, our standard error of the mean. That's so whereas population standard deviation is the average spread in the population, the population standard error of the mean is the average spread for the sampling distribution of means. Now, once we're done with that, we can understand that any form of S squared is our sample variance. And any form of S is our sample standard deviation. Again, now this is the average spread for our sample. If we take this with a little X bar or D bar or X bar minus X bar 2, X bar 1 minus X bar 2, it's a standard error again, this time for the sample. So sampling distribution of means for a sample. Take that sample many, many, many times. Take the average of each one of those samples and plot it. That's how we get our sampling distribution of means, if you remember. This is the average spread for our sampling distribution of means. And not surprisingly, it is going to be smaller than our sample standard deviation. Because what do we do with our sample standard deviation? We take it over the square root of n. So one more word I just want to share is that basically what's going on in 3 of the 4 tests, Z-test, T-test for a single sample, and T-test for dependent samples. You're getting a variance or SD, you're getting your standard error, then you're getting your Z or T. Okay. Now for Z, you're actually always given your variance, so you don't even have to worry about it. For t-test for independent samples, it's got one more little step in there. Because even if you're given your variances for group 1 and group 2, you still got to pool them together or combine them together into an S-squared pooled. Then you get your standard error. Then you get your T. Okay.
I just had one more question about this slide.
Sure.
What about the mu of x and the sigma squared of x? They were under the characteristic sampling distribution of means.
Oh, yeah, they pretty much only stay there. Yeah, so mu of x bar would be the mean for the sampling distribution of means, and it's the same as your population mean. So mu of x bar was for the sampling distribution of means. So even though it gets really thin, it has the same mean as your population mean. And what was the other one you said?
Sigma squared of x bar.
Okay, yeah, technically you could have that. That's the variance for the distribution of means. It doesn't really come up. Neither of those really come up aside from just understanding what they basically are, but they don't come up in our Z or T formulas. But it is good to have a basic understanding of what they are. So the variance is going to be smaller. The variance of your sampling distribution of means is going to be smaller than your plain old variance. But I wouldn't worry about how to calculate that one.
Okay, so this, you said variance sampling distribution of means is smaller than your variance?
Yes.
And like smaller than the variance of the population?
And I'm sorry, say that one more time.
You said it's smaller than the variance. Is that the variance of the population?
Yes, yes, yes.
Okay, thank you.
Of course, of course. And then these are some less confusing symbols, which I'll just, again, they're in the slideshow that I put up this morning, but N stands for sample size. I think most of these are okay from, but I think it's the other group that gets people. But if there's any of these you want to talk about, just let me know. And I need to end us in just a moment here, but is there any other questions I can answer for any of you before I do?
Is there a way that you could possibly post all the slides that like are gonna be on exam 2?
That's a good question. And I haven't
Like from
historically
the
done
lecture?
that. Yeah, I know from the lectures. Yeah, I can do that for you guys. I'll post them. And I'll post this, what we just did today, under YouTube. So look for that on YouTube if you want to look at this talk today.
Okay, thank you.
Yeah. Okay, anything else? Okay, I'm going to end it for today. But I'll be here Monday. And if you have any additional questions, you can ask them then. We'll be also dealing with questions about, I think, our first one-way ANOVA thing, but that's okay. We could still take questions about the exam as well. So have a great weekend, and I'll see you guys later.